In this video, we're going to cover the basics of PC architecture and networks. We're not going to go into a great detail, but it's important to know the principles so that when we start looking at threats and vulnerabilities, you'll understand some context for what we're talking about. This picture is sort of an illustration of a vulnerability that most people don't recognize. And although it's based around cats, the site actually illustrates an important phenomenon of information leakage. These are images that have been uploaded to the internet, mostly Flickr, but other services, and they've been harvested by this site. And essentially they're pictures of cats, but they use the GPS information, the geolocation, that is embedded in these photos to actually track down where the images came from. So even though it says, "I know where your cat lives," it illustrates the point that when we share photos, that we're unwittingly sharing a lot more information about our private lives. Now, organizations like Facebook and other social media platforms do tend to strip out that information now, even if you do upload it. But it's good to know that those media sites actually have access to that information. So in this video, we're going to cover fundamentals and language of computer hardware and operating systems, how those operating systems implement security features, and then look at fundamentals of networking and network security. Now, as I said, this is a very brief overview. We'll touch on these points as we progress through the unit, but for this video we just want to cover the basic language. Although we were focused on general ideas around cybersecurity, it's useful at least to have some understanding of computers and the networks that they use to communicate over. So we'll look at PC architecture first in a generalized way, and then look at the basics of how computer networks operate, especially the protocol TCP/IP that is the basis for all communication on the internet. At one level of abstraction, a PC's purpose is just to run software applications. So those applications are run by an operating system, so for example Windows or Linux or Mac OS. And before an operating system can run, it needs to be loaded and started, and this is the job of a piece of software called the bootloader, which is part of the firmware of a computer. Firmware exists in devices like hard drives, network cards, sound cards, etc. It's essentially software that has been embedded in a chip and implemented in a device. This is all running on hardware, which are the components of the PC that store, execute, and process inputs and outputs. So you can see the sort of layers there of hardware, which enables the firmware to run, and then on top of that has an operating system that then interfaces with applications that you use to carry out some functions. So this is a image of a typical PC and the various components in this. We can see starting at the top that we have a power unit, power supply unit, PSU. We have CD drives and potentially hard drives. Oh, here is a hard drive here. Then we have the motherboard, which contains all of the processing and memory apparatus. So the CPU, central processing unit, which is responsible for the operations of a computer, so essentially the brains. RAM, which is the memory, one type of memory that is stored, that is used on the computer. And then other pieces of equipment like a fan. The CPU is going to generate quite a lot of heat, and so the fan is there to keep that cool. Now, in more sophisticated setups, we'll have a potentially liquid cooling of the CPU and also potentially the video card. So the video card is the thing that drives your display and manages that. So there's all these different components. There's also a network card, which is not shown here, that will allow you to communicate either over a wired connection or wireless. And that's the basic architecture. So all PCs, laptops are based on the same sort of architecture. Obviously, a laptop is all squashed into a smaller space. So the CPU processes instructions and data that are stored in memory. So memory is either random access memory or read-only memory. RAM can be written to. Read-only memory is, as it says, read-only. Instructions and data for applications are transported between memory and the CPU over what's called a bus. And there are three different types of buses in a computer: an address bus, a data bus, and a control bus. So an address bus will basically communicate the addresses of instructions and memory. Data buses will communicate the data that is fetched from memory or disk. And the control bus is something that will then control peripherals and other devices by basically telling them when they can be written to or read from and other things. The CPU can also read and write data from input-output devices, so that might include things like printers, for example, or other devices that you've connected through to the computer. Instructions that are processed by the CPU are based on simple operations like add, subtract, and then the logical operators and, or, and XOR, etc. This is part of an instruction set, and depending on the chip, the instruction set will be slightly different. So we've been dealing with Intel chips in the Windows and or Intel and AMD chips that are in Windows and Macs, and ARM-based chips that are in the Apple Silicon or Apple M1, but also in some Windows ARM devices. So when a computer is powered on, the firmware in the read-only memory is loaded and run. This is what's called the BIOS. Some of you might have come across this already when trying to install Docker and having to make changes to the BIOS settings to allow for virtualization to run. Hopefully most of you didn't have to do this because it was set by default. The BIOS is the basic input-output system, and this is what the first thing that runs when a computer is powered on. So it will run a power on self-test, a post, to check for hardware components like a display, keyboard, network card, and memory. If any of that is missing, then the post will fail. Typically in older computers, you might have come across or experienced a situation where it used to have batteries for keeping clocks going, for example, on the computer, and the post might fail when the battery had run out of power. The BIOS will then load the first 512 bytes from the hard drive, and that's called the master boot record. And this contains the bootloader code that will execute and load the operating system. So essentially we check all of the hardware components and then go to load the operating system for a known location on the disk. If it can't find it, then again that process will fail. So the operating system itself is responsible for a number of different tasks. The first is running and scheduling applications, and it has to schedule those to share resources such as the central processing unit, CPU, disk, and memory. It allows for memory virtualization, so this takes the memory that you have got in your machine and expands it so that all applications can address a larger amount of memory. And this it does by essentially mapping that virtual memory to physical memory. The operating system controls access to I/O devices through I/O drivers, and you will have come across that on occasion when you've updated hardware and you need to, especially on Windows, update drivers. It's not unknown of in Macs, but the Mac deals with that a lot more seamlessly than Windows does. The operating system will also manage access control and authentication and handle communication via networks. And finally, it handles graphical user interfaces. So it does other things, but those are the basic system functions that an operating system will be responsible for. As part of the operating system, there is a kernel, and the kernel is essentially the privileged mode of certain applications that run and control all of the functions that we outlined before. So the CPU operates in different modes, user mode and supervisor mode. Applications are then run in different protective rings organized from the most secure and privileged in ring 0 to application level code in ring 4. Applications that are scheduled to run are prioritized depending on which ring they run in. Most privileged applications have priority. Organizing the kernel in ring 0 is a protection mechanism to allow only trusted code to run there. So essentially, you can see on the right the diagram there. We've got the operating system, which is essentially operating in multiple rings, but ring 0, 1, 2, and 2, because the device drivers can be considered part of the operating system. But the kernel, the basic privileged mode functions of the operating system run in ring 0, and they're protected from applications that run in the outer ring. So the way that this operates is that applications that need to actually communicate with the operating system need to request the privilege to be able to do that, and then the kernel will operate and do actions on applications' behalf and then return that function to them. So another component of a computer is the file system, where all of your data is stored. And essentially, this is a system that organizes files. And a file is a named collection of information stored on a storage device, such as an internal disk drive or external USB drive. It contains or has metadata, such as its name, the type of file it is, location, size, protection, and other information about who created it, when it was created, updated, etc. A file will normally have an owner and permissions that are associated with access control, who can access that file. So files are organized in directories or folders, depending on the sort of naming conventions. And the operating system will support a file system, which is a way of organizing these files on a disk and provide then the basic operations of creating files, reading from them, writing, and deleting them. So devices that provide these sort of operations can be viewed as files as well. So Linux in particular basically treats all devices as files, and so when you read and write to a device, you can actually just treat it as if you were reading and writing to a file. And there are essentially structures on the disk, on the file system itself, that you can access that are essentially interfaces then to those devices. So there's numerous different types of file systems, and you'll again have come across some of these if you've ever formatted a USB drive, for example. And over the years, it's progressed from early DOS and Windows file systems that used FAT and FAT32 through to NTFS, APFS, which is run on Apple file system, EXT on Linux, etc. So there's a whole series of these. And access to files is controlled by discretionary and role-based access control, as we sort of mentioned in a previous video. So let's talk about processors. The operating system is responsible for running programs and managing their access to system resources. So when a program is run, it's known as a process, and multiple processes may be running at the same time, And so obviously they have to share access to resources like the CPU, to memory, to disk. You can't have all of them running at the same time because a CPU only processes one set of instructions at a time. And so the operating system handles this by running a scheduler. The process itself may be in a number of different states depending on what actions it's performing and whether it has used up an allocated amount of time that is allocated to it. So in the right here we have a diagram which illustrates the different processor states. So we start off with a new process that enters the ready state. So that means that the program or process is ready to run. The operating system, when it's actually sort of saying that it can run, will schedule or dispatch it to run, and then it runs for a period of time. That will continue until an allocated amount of time, the time quantum, is used up, or the process decides to do an I/O request, in which case it will wait for that I/O request to complete, and so it may block at that point. And if it does, then it can go into a suspended state where it waits, and then eventually that will return and resume to wait, or it can go to a suspended ready state and then go back into ready for running. At the end of the process, when the process is finished doing what it needs to do or exits, it can go into a termination state. Important to note that the suspend state is also known as a sleep state. So, just to recap that, processes are scheduled by the operating system according to one of a number of different algorithms. The processors may run at the same time if the computer has multiple processors. So this is actually common in a lot of computers at the moment, that they'll have multiple processors, and that does allow you to run multiple processors at the same time. We can also do this on a simultaneous execution through multi-threading of an application, so that's a lightweight version of a process. And of course, processors, CPUs, also have the concept of a hyperthread, which allows multiple threads to run at the same time. It's sort of a lower level simulation of having multiple processors. So I mentioned the states already, but we'll just recap that. The start is the initial state when a processor first started or created. Ready is when the process is waiting to be assigned to a processor, and they have a processor allocated to them by the operating system so that it can run, and they may come into this state after the start date or while running, may be interrupted by the scheduler to assign CPU to some other process. So the process can then be running and or waiting for a resource, and then finally it can exit when it's done its processing, or the user exits the application, for example. So a process will have a number of attributes, the principal one being a process ID, which is used to uniquely identify it, and that's a number. A process will always have a parent, so processes are started by other processes, and the first parent is essentially the operating system. There will be a specific application that is responsible for launching all other applications in the operating system on the computer. And so, but if you're in a bash shell, for example, and you run a process, then the parent of that process will be the bash shell itself, and we'll explore that a bit in the lab. So the parent can be identified by the process parent ID, the PPID, and you can get access to that depending on whether you're in Windows or Bash in a number of different ways. So files Processors work on files and devices that are represented as files, and so information about these are kept for each process, and also virtual memory. So processors are allocated memory to store the code and the data that it operates on, and essentially if this becomes too large for physical memory, it may be mapped to disk, but it's the responsibility of the operating system to manage the virtual memory space.